Good morning. Today we'll discuss linear regression. In linear regression, we have two linear regression. One is simple linear regression, other one is multiple linear regressions. So in this presentation, we will discuss simple linear regression. Simple linear regression is the analysis which include a single explanatory variables. So based on the number of explanatory variables, the linear regression can be classified. Scatter plot provide a graphical indications of relationship whether they are linear or non-linear or essentially non-existent. We have another one as the correlations. The correlations are numerical summary measures that indicate the strength of linear relationship between pairs of variables. The correlation between a pair of variables is a single number. So why we are taking here a single number? Why? Because it is a simple linear regression that summarizes the information in a scatter plot. A correlation can be very useful, but it has an important limitations. So there all it measures only the strength of the linear relationship, and if there is a non-linear relationship as suggested by the scatter plot, the correlation can be completely misleading. So scatter plots and the correlations are very useful for indicating linear relationship and the strength of this relationship, but they do not actually quantify the relationship. A simple linear regression where there is a single explanatory variable which I have already defined. The relationship between the dependent variable sales and the explanatory variable promote must be quantified. In simple linear regression, it is very important we need to quantify. So here, the fitting a straight line through the scatter plot of the dependent variable y versus the explanatory variable x, and then biasing will quantify this relationship. Okay. Here we have fitting lines in the scatter plot that will try to quantify the relationship between two variables like x and y, but we have a number of straight lines. So we should identify which straight line and which straight line addresses which issues. So that must be identified. Least square estimation. So there is one least square estimation. By estimating this least square, we will try to reduce the error in simple linear regressions. Here there is one fitted value. It is the predicted value of the dependent variable. Graphically, it is the height of the line above a given explanatory values. We will see in the graph. The corresponding residue is the difference between actual and fitted values of the dependent variable. Okay. So here we have dependent variable, the difference will be defined over here. The scatter plot between sales and promote repeated in figure 10.2 is given in the next slide. Hint at a linear relationship between these two variables. It could not be difficult to draw the straight line through these points to produce a reasonable good fit. In fact, a possible linear fit is indicated in the graph. See here, in x-axis we have taken promotion data. In y-axis we have taken sales data. So these two variables, it is given over here. We are going to identify the relationship between these two variables through linear regressions. It is simple. Here sales versus promoter. Here all the data were plotted here as a data point. There is no possible way to draw this straight line. So approximately if you choose the points, data points, and if you draw the straight line, that will try to define the relationship between these two variables like the sales and promote. The vertical distance from the horizontal axis to any point, remember, which is just the value of the sales for that point, can be decomposed into two parts. One is the vertical distance for the horizontal axis to the line. Horizontal axis to line. Other one is vertical distance from the line to that point. So these are the two parts. The first of these is called the fitted value. So fitted value is the horizontal axis to the line. And the second is called residue. Residue is nothing but the distance, the vertical distance from the line to the point. So it is above the line. The relationship is not perfect. Not all of the points lies exactly on the same line. So if you look at the previous graph, all the lines is not there in the, see here, if you look at this straight line, all the points are not available in the same straight line itself. So there are some variations. So it is not so perfect. The differences are the residuals. They show how much the observed values differ from the fitted values. If you know what do you mean by observed value or what do you mean with observed values and fitted values. If a particular residue is a positive, the corresponding point is above the line. Okay, so the point which is available in the above line is called the residue. Okay, if it is a negative, the point is below the line. If it is above, it is a positive. If it is below, it is a negative with respect to the line. So the only time of residue is the zero, is if the point lies directly on the line. The relationship between observed values, fitted values, and residues are very general and is stated in equations. So the fundamental equations for regression will be defined like that: observed value equal to fitted value plus residue. See, this is a straight line. This is drawn. Okay, this straight line it will define the relationship between promotion and sales. Okay, and here there are some points. Here one point, here another point, here one point. Okay, so with this point, we'll see the relationship. Will define the different values. See here, the line is under this line. Under this line, we have point over here. This will be called as fitted value. With this point only, the fitted value will be defined. So the fitted value will be the distance between promote and this line. Okay, and the above the line, you have above the line. Okay, so this will be residue. So residues. Okay, so if the points which is above the line will be defined as a positive residues. So the points which is below the line will be called as negative residues. So this is the proposed straight line fit. How to choose the best fitting line through the points in the scatter plot? Okay, the answer is it is the line with the smallest sum of squared residues. We know what you mean by residues. Okay. The resulting line is called least square line. Okay. Remember, it is the line with the smallest sum of squared residues. Okay. So the maximum possible lines should lie on the line itself. Why do we use this sum of squared residues? Why not minimize some other measures of the residues? Why? Because the least square line has the property that the sum of the residues is always exactly 0. Okay. So to adjust this, we could minimize the sum of the absolute value of the residues and is a perfectly reasonable procedure. The least square is one of the very important one. The least square line is the line that minimize the sum of the squared residues. It is the line quoted in the regression output. So here you can see the statistical software package is available for everything that will perform everything automatically with respect to minimizations. So the formula for the least square line is given y equal to a plus bx. Here a is the y-intercept of the line, and the value of y uh, x equal to 0 and b is the slope of the line. The change in y when x increases by 1 unit. So therefore least square line is specified completely by its slope and intercept. So for all these things, the formula is given from the formula on the right of the B. You can see that is closely related to the correlation between x and y. And specifically the standard deviations x, y, x are kept standard deviation of x and x y of x and y are kept constant. The slope b of the least square line varies directly with the correlation between the two variables. Okay, so the effect of formula for the a is not quite as interesting. It simply forces the least square line to go through the point of simple means. This is the formula which is given over here. This first formula is the equation for slope in simple linear regressions. The second one, equation for intercept in simple linear regressions. See, all the variables are defined in the previous slides itself. Okay, so by applying this value for this each and every variable, you will be able to identify the slope in the linear regressions as well as the intercept in the simple linear regressions. Thank you.